Hello and welcome. Today we're going to spend a wee while talking about probability. Now, we all probably know what probability is, but we want to spend a few minutes just actually thinking about it in the context of statistics and thinking about it in the context of how we measure things and what does chance play in our measurement processes. Well, in fact, statistics, the actual core under stats, is really probability or chance, and we use chance all the time to give ourselves a basis for the analysis of data. What chance are we talking? We are talking what is the chance of our sample, what's the chance of it, or the probability of it, with a P, representing our population. And in reality, that is what this probability factor is. The other way we see it used in statistics is if we have two samples, like this, our question is, what is the probability that these two samples are not the same? So that's, again, one of the core questions that we're always asking. If we give group 1 a drug and we give group 2 a different drug and we come to some statistical arrangement, what is the probability that one drug is better than the other? So probability is at the core of most of statistics and is at the core of how we read and understand statistics. And I think probably my greatest input that I can give you today is what we call a normal distribution curve. Very poorly drawn by me, by hand. But what is this? What does this represent? Well, this actually represents a probability curve. So this is about probability as well. What is the probable chance that a particular sample is situated or has a value nearby to the central core tendency of the population? So normal distributions are really measures of probability, and this curve is about chance. So probability sits at the very centre of statistical analysis. And you know about probability. You're always asking the question, for example, patients in the most dramatic situation are asking things like, for example, what is the chance of 5-year survival? Is it a 30% chance or is it a 90% chance? So your patients will actually be asking you, if I take this drug, what is the chance I'm going to get better? So healthcare, and I know this sounds really brutal and you don't probably want to listen to this, but when you get to my age in this process, you actually start to really recognise that healthcare is a process of chance. It's a process of tipping odds. And you start to recognise, for example, what does a drug actually do? Well, a drug is tipping the odds of a condition getting better towards your favour. And I laugh with many of my students that what does a drug actually do for you? A drug is like putting your toe under the leg of the table that holds the roulette wheel at the casino. Now, I know that's a very brutal and simplistic view, but in reality, much of what we do is just about tipping the odds, isn't it? Think about it in a very simple form. Think about it at the traffic lights. When you stop at the traffic lights next time on a red light, or you drive off on a green light, what are you doing? Well, the traffic lights are asking people to change the odds of a collision in the middle of the intersect. If everyone follows the signals, then your odds of having an accident are diminished to zero. So traffic lights and daily life is about shifting odds. So understand that probability is about odds. So before we go on and talk about normal distributions and how probability applies to statistics, I want to spend a few minutes talking about sampling. Because sampling, the way we collect a sample and the arrangement of that sample is critical to the way probability will then play out in our calculations in our statistical calculations beyond that sample. So it's really important for us to understand clearly and be able to enunciate the process in which we collect data and the sampling that we have used to produce our data set. And to collect data in the first place is called sampling. And sampling can really happen in a few ways. The most obvious sample is to take a total population. So let's imagine that you wanting to, like I said before, understand the height of Australia. The ultimate sample is to take all 22 million people and actually measure the height of individuals. Now clearly this has problems. To start with, the cost of measuring an entire population is often prohibitive, and there are other prohibitive factors in those sorts of analysis when you're trying to collect an entire population's data. So obviously over the years there has had to be a process of development of other methodologies to do it. And what we've basically come down to is a method of sampling that total population and then taking that data and saying, well, what can we infer from this sample? And there is a number of ways of actually doing a sample. Obviously the first methodology is what's described as a random sample. And a random sample is relatively simple to understand. That's a sample where you say, look, I'll get a random number generator and we'll give every Australian a number, and whatever number comes up in the random number generator, we'll measure those people and use that as a sampling process to give us a subset of the population. And being a random subset, we hope that sample is a reasonable estimate of the total population. And there are a whole bunch of statistical tests we can then use on that sample to actually test whether it's a good representation or not. Sometimes in a sampling process we use what's called a stratified random sample. And the best example I can give of this is, let's say we're doing the height story again of Australians. Clearly kids are going to mess up the statistics because they're shorter than the adults. So what you might do is you might say, let's have a collection of everyone from 5 to 10 years old, from 11 to 15 years old, from 16 to 20 years old, etc., and actually measure a sample in each of these. So this would be called a stratified sample in the sense that it's stratified your population into clusters and then taken random choices within that stratification. So they are really fundamentals of sampling a population. Clearly there are some ones to avoid, and the first and most obvious one to avoid is what we call a judgement sample. And look, I'm sure you can work that out for yourself. If I walked in and I knew that all the kids who sat on the left of this classroom had high decay rates, so therefore I chose for my sample of dental decay all the kids who sat on the left of the room, I'd get an outcome that was clearly inappropriate. So a judgment sample rests on the problem of a known condition mix, in a sense, for clinicians, and knowing where that sample is and picking off the type that you want out of it. The second type that we try to avoid is called a convenience sample. And a convenience sample is again runs high risks of not being random enough to give you a reasonable sample. And a convenience sample is usually things such as the classic exemplar of a convenience sample is that a school teacher gives permission for one class to be involved. We'll put an L in class, shall we? One class to be involved, but clearly you can't then extrapolate the data from that one class to an entire population. It may be that that's a special, unique group of children, so convenience samples are also seen as not actually reasonable processes for collecting a sample of data. And clearly the last thing to keep in mind is when you collect data, if you've chosen a protocol by which you collect data, you need to stick to the protocol. I've reviewed many papers in my career where people have gone, look, we started out with a random sample, but we knew that we weren't getting enough children, so a couple of teachers from the school down the road said we could look at the children in that classroom, so therefore we went and did that. Well, you've now contaminated of methodology. You've now got a contaminated methodology, and most journals that won't even get to review stage. So once you start contaminating the methodology with non-random sampling, and in particular once you move from your agreed protocol to a new protocol, you run yourself a risk in all sorts of frameworks for getting into strife, not least by which being that you're now not following the ethical application that you probably put in the first place that required you to articulate the sampling process you were going to use. So now with that interlude about sample, let's just go back to our normal curve and have a think about probability again and what it represents in a curve. In our normal distribution curve, and I'm going to put the midline in here, what we do is a normal distribution curve actually represents the total population. So the area under the curve represents 100% of the population. And then what we know from our probability and from our statistics is that if we go out one standard deviation this way and we go out one standard deviation in this direction, we can tell that in this region, in that region there, sits about 68% of the population. And we know if we go further out around this curve, if we go out 2 standard deviations, and calculate all of this area right through to here, we know that the yellow area is about 95% of the population will fall in that, and I'm not going to draw it in, but that's another standard deviation there. I won't draw it in, but just to complete the story, if you go out another standard deviation, out here, we know that about 97% of the population will fit within 3 standard deviations of the curve. Now, this is the way we talk because we're trying to use our sample to be inside the curve. Just out of interest, You may have heard in the physics world in this last 12 months, we think that the boson, the Higgs boson, has been found, and the measures that they use in physics are called sigma, 6 sigma. And what 6 sigma means, or the sigma factor, means that they're going for way outside the normal curve. They're looking for 6 standard deviations away from the middle of the curve as evidence. In physics, they're looking for evidence that it sits outside the curve. So in other words, it's not what we normally see with other particles in the case of the Higgs boson, but it's so far away from the middle that it has to be unique and special on its own. So please don't get caught up all the time in 1, 2 or 3 standard deviations that we use. Many other disciplines use this same sort of probabilistic approach to understanding a sample, but some of those disciplines are actually looking for outside that, at extreme ranges of proof of evidence that something exists. So that's where we're going to stop the short description of probability and what it means. Hazard to remind you that the core to this story is about a normal distribution curve and the proportion of the population that sits within that curve or around that curve. Thank you.